Welcome to Math with Professor V. In this video, I'm going to solve the final exam that I gave my Elementary Differential Equations class this semester, spring 2025. There were 10 questions, 10 points each, and then I did put 3 extra credit. I don't think anyone finished them all. I haven't finished grading the exams yet, but we're just going to jump right in. I'm not going to give like a super in-depth lecture or background as I'm solving. I'm just going to say what kind of differential equation it is and then just solve. If you need more of an in-depth explanation on any of the techniques or topics, then just check out all the videos that are linked in the description. Okay, here we go. So use any appropriate method to solve the differential equation. So starting off, if you notice, this is higher order. So this is order 4 differential equation with all constant coefficients and it's homogeneous. So I'm going to find the characteristic equation and then solve from there. So remember, to start off, we assume a solution of the form y equals e to the mx. And then when you make the appropriate substitutions, which we usually don't have to write out anymore, then the characteristic equation is m to the 4th plus m cubed plus m squared, and that all equals 0. This is just a homogeneous differential equation here. So our goal now is to solve and find the roots of the characteristic equation. I can factor out m squared, and then I have m squared plus m plus 1 is 0. So m squared outside means I have 0 as a root repeated. And then this trinomial here does not factor, so time to bust out our trusty quadratic formula. Still using it all these years later. So m equals -1 plus or minus square root of 1 squared minus 4 times 1 times 1 all over 2. So this is -1 plus or minus I root 3 over 2. And we want to be able to separate the real from the imaginary part so we can identify alpha and beta and set up our solution appropriately. So let's rewrite this as -1/2 plus or minus I root 3 over 2. So the real part we often refer to as alpha, and the coefficient of the imaginary part is what we call beta. So now let's construct our solution. Notice, again, this was order 4 differential equations. We should have 4 terms in our solution, just like we had 4 roots to our characteristic equation. 1, 2, plus or minus is 3, 4. So here we go. You're going to have y equals c1 e to the 0 for this guy, plus c2x, because this is a duplicated root, e to the 0, plus, then we have e to the alpha x, so e to the -1/2 x times c3 cosine beta x, root 3 over 2, plus c4 sine beta x, sine root 3 over 2. So we can clean up a little bit. Obviously, e to the 0, that's just going to be 1. And then it's kind of up to you or your instructor if they have a preference. I would say just leave this factored out, the e to the -1/2 x. I'll just write it as e to the -x over 2. So c1 plus c2x plus e to the -x over 2. And we can leave these trig functions in here. Oops, how did I forget the x's? Wowza, you were probably screaming at me through the screen. My apologies. Okay, very good. So that's the first one done. Boom. Okay, moving on now. Use any appropriate method to solve the differential equation. Looking at this equation at first glance, hopefully you'll observe that it is homogeneous. So I'm going to solve it by making the substitution where we let y equal u times x. So dy is u dx plus x du. And then my goal is to make this equation separable in terms of x and u. So here we go. Y is ux plus x times cotangent. Y over x is ux over x dx minus x, and then now this dy is all of this, so u dx plus x du, and that is 0. Okay, so let's simplify now. So those x's will cancel out. Also, I can cancel out an x from the entire equation. This x can cancel, this x can cancel. So if I'm dividing by x, I know x can't be 0. So I have to pick an interval on which my solution is valid. So you have to pick only one interval, you only get to pick one. An interval that excludes where x is 0. So your choices are either the interval from -infinity to 0 or from 0 to infinity. Now things work out much nicer when you choose this interval, so that's what everybody chooses. Because then later on, if we have any absolute value bars around x or something, we can just drop them because we know everything's going to be positive over there. So that's the interval I'm choosing, but you should state it, okay? I told them if they didn't on the test this time, I wasn't going to dock them. I know the paranoia was real. Okay, so these are all canceled out. And then I'm also going to distribute at the same time in the next line. So we'll have u dx plus cotangent u dx minus u dx minus x du is 0. Good? Beautiful. And then u dx cancels as well. Oh me, oh my. So we have cotangent u dx equals x du. Now we're going to make this separable. So 1 over x dx equals 1 over cotangent u would be tangent u du. Fabulous. Now we can integrate both sides. So ln absolute value of x equals ln absolute value secant u plus c. Now I don't need the absolute value on x because remember we chose the interval from 0 to infinity. So I can drop them in the next line if I want. All right. Now I'll have ln x equals ln, you do need the absolute value here, secant y over x, very good, plus c. I'm subbing back in. So if you'll notice when we made the substitution right here, let y equal u times x, u is y divided by x. So that's where that came from. And then now what I'm going to do is take e, raise it to both sides of the equation, but please be careful. Left hand side we're going to have x equals secant, I'll put absolute value for now, y over x times e to the c. Oh yeah, don't forget that part. Okay, so note e to the a plus b is e to the a times e to the b. Yes? Okay, so think of it this way. All of this is a, all of this is b. So it's going to simplify as e to the a. So those will cancel out. I'm just left with absolute value secant y over x times e to the c. Are we good? Okay, then how to clean up your final answer. Let's rename our constant something cute. I don't want to have e to the c in the final answer. And then remember, when you drop absolute value bars, you put a plus or minus in your equation. So I could really write this as x equals plus or minus e to the c times secant of y over x. Well, how about I call my new constant k plus or minus e to the c. That'll look beautiful. So then we could say we have x equals k secant y over x. You know what would look so fab? Move the secant y over x to the other side, and you would have x times cosine of y over x equals k. So either one of those is considered completely simplified, but also make sure part of the answer has to include where you renamed the constant. And if you're going to drop the absolute value here, you need to put plus or minus. Okay? Beautiful. Moving on. Use any appropriate method to solve the differential equation. So, you know, this test is all jumbled up. They didn't know what technique to use where always. It's first order. So you're thinking back to the beginning unit. It's not going to be homogeneous. And it's not exact if you check. No, so sorry. It's actually linear. Yes. But it's linear treating y as the independent variable because notice we have this y e to the y situation. So actually the form that we're going to have to rearrange it in first before we find the integrating factor is going to be dx dy plus p of y times x equals q of y. So first, let's divide the whole equation through by dy. That way I can see the derivative, dx dy, appear, and then we'll strategize from there. Sound good? So we've got y times dx dy plus xy plus 2x minus y e to the y is 0. So from here, notice my derivative needs to be isolated. So let me divide everything through by y now. So we've got dx dy plus x plus 2x over y minus e to the y is 0. And then look at this form. If you need to write it out, it's helpful because traditionally, you know, we do them where x is the independent variable. I need to factor out all the terms that involve y that are being multiplied by x to the first. So that'll be here. And you might say, wait, Professor V, there's no y involved here. I know, but we're going to factor out the x. There can only be one x in this entire equation. You have dx dy, that doesn't count, but x to the first, that's what makes it linear. So we're going to factor it out. These terms will stay here, and then q of y is going to be this e to the y once I move it over. So watch this. We've got dx dy plus p of y is 1 plus 2 over y times x equals e to the y. Are we okay? All right, good. Now at this step, you need to identify the interval on which your solution is going to be valid. In this case, it's an interval for y. And notice y cannot be 0. So you have to pick, let's pick from 0 to infinity. Okay. All right, let's find our integrating factor, mu. In this case, it's going to be e raised to the integral of 1 plus 2 over y dy. So that's going to be e raised to the y plus 2 ln. I don't need to put absolute value of y because what did we just say? We're on the interval from 0 to infinity. Oh, perfect. And then, time to use our exponent properties. E to the y times e to the ln of y squared. Yep. And then that's going to give us y squared e to the y. So that's our integrating factor. Now come through, multiply the differential equation right here by your integrating factor. So now we'll have dx dy times y squared e to the y plus y squared, y squared plus 2 times y e to the y x equals y squared e to the y times e to the y, so that'll make it e to the 2y. All right, good. Now let's verify, is this the derivative with respect to y of my integrating factor times x? So is it x times y squared e to the y? Always check because I've caught many a mistake at this step here. So we would do the product rule, derivative of x, leave this guy alone, plus, now take the derivative of y squared e to the y, we would have to do the product rule. So y squared times e to the y plus 2y e to the y, perfect, leave x alone. Everything checks out. Integrate both sides with respect to y. So left-hand side will just have xy squared e to the y. Right-hand side, how should we evaluate this integral? Let's use tabular method for by parts. Much more slick than doing a bunch of rounds of by parts. So put the polynomial function in the column that you differentiate, y squared 2y, keep going till you get 0, and then e to the 2y is I, we're going to keep integrating it. So 1/2 e to the 2y, 1/4 e to the 2y, 1/8 e to the 2y, then you take products on the diagonal, and then the signs alternate, so add an extra plus, minus, plus, and that'll be it. So let's see. Probably need to scoot this guy over. 1/2 y squared e to the 2y minus, I'm taking this product now, it'll be negative 1/2 y e to the 2y plus 1/4 e to the 2y. Now let's put the plus c in. And then last thing I'll do, let's get x by itself. So let me divide by y squared e to the y. So x equals 1/2, just e to the y now, minus 1/2y e to the y plus 1/4y squared e to the y plus, just to make the last term look similar to the others, let me write it as c over y squared e to the negative y. Okay, that one's done. It's, it's not difficult when when you're doing your homework, like, oh, this section is all linear differential equations. But then when it's on an exam and they're jumbled up, you got to kind of run through in your head, is it homogeneous? No. Is it exact? No. So then you think maybe it's not separable. Then you try maybe linear. But remember, the key is this is just first order, so it's going to be one of those. Don't start trying to Laplace it. I guess maybe you could, but I wouldn't. Okay. Plus, I gave you no initial conditions. It would be hard. Speaking of Laplace transform, well, Laplace really shines when it's time to evaluate differential equations involving the unit step function, like the one we have here. So use any appropriate method to solve the differential equation. We have y double prime plus 4y equals sine of t times u of t minus 2 pi. And then here's our initial conditions. Y of 0 is 1 and y prime of 0 is 0. So remember first, before we're going to take Laplace transform of some function that involves the unit step function, the argument needs to match. So since we have u of t minus 2 pi, I need this to also be t minus 2 pi. Convenient for us, the period on sine is 2 pi, so I don't have to manipulate with any identities or anything like that. I can just simply replace the t with t minus 2 pi and their equivalent, and I can just be on my merry little way. That was lucky for us. We're not always so lucky. I worked through plenty of examples in the video lecture on Laplace transform with unit step function where I show what to do if it's not so nice, okay? Anyways, let's take the Laplace transform of the differential equation. So Laplace transform of y double prime plus 4 times Laplace transform of y equals Laplace transform of sine of t minus 2 pi times u of t minus 2 pi. So first term, Laplace transform of y double prime is s squared y of s minus s times y of 0 minus y prime of 0 plus 4 times Laplace transform of y is just y of s. And then here we need to use our second translation theorem. So we'll have e to the negative 2 pi s over s squared plus 1. Good? Okay, so it's always e to the negative cs. In this case, c is 2 pi. And then you do your normal Laplace transform of sine t, which is just going to be 1 over s squared plus 1. All right, let's substitute in our initial conditions now. Y of 0 is 1, so that's a 1. And then y prime of 0 is 0, so that's gone. Okay, so what do we have now? S squared y of s minus s plus 4y of s. I got too excited. 4y of s is e to the negative 2 pi s over s squared plus 1. Let me factor out y of s, and then we'll have s squared plus 4 equals e to the negative 2 pi s over s squared plus 1 plus s. And then let's divide everybody by s squared plus 4. Then I'm already thinking to myself, okay, how am I going to take inverse Laplace of everybody on the right-hand side? I need to do partial fraction decomp for this first term. The second one, though, we're good to go. I can just multiply and divide by 2, right? And we'll be in business. But I need to do partial fractions for this term. I would not recommend doing convolution theorem, but some of my students, they're so bored of partial fractions, they got carried away. They did a lot of convolution theorem by choice. I don't know, though. It's not always more efficient, guys. So 1 over s squared plus 1 times 1 over s squared plus 4. Both of those are irreducible quadratics. So the decomp will have the form as plus b over s squared plus 1 plus cs plus d over s squared plus 4. I won't bore you with solving it. At this point, this should be no big deal for you. A is 0, c is 0, b is a third, and d is negative 1/3. Okay, then I just kind of jump to taking inverse Laplace and using my decomposition. So y of t is going to be inverse Laplace of y of s. So that's going to be inverse Laplace of, we've got 1/3, because a is 0. So 1/3 over s squared plus 1 times e to the negative 2 pi s minus, since d is negative, 1/3 over s squared plus 4 e to the negative 2 pi s. And then inverse Laplace of this last term, like I said, we're just going to have to manipulate with some constants. So this is s over s squared plus 4. Oh, no, we don't. Just kidding. There's an s up top. We're golden. Okay. All right, now let's start taking the inverse Laplace of everything we have here. So e to the negative 2 pi s means we're going to translate all of our t's to t minus 2 pi and slap on u of t minus 2 pi. Okay? All right, very good. So we're going to have here, there's no s up top, so inverse Laplace of this term is just going to be sine of 1 times t. There's an extra 1/3 in the front. That's fine. So we'll have 1/3 sine of t minus 2 pi. Don't forget to translate that part. Minus, now here again, k is 2, right? 2 squared is 4. So inverse Laplace would be sine 2t if I had a 2 up top. So we need to add that in there. And then I have to multiply by a half. So I'm going to be left with an extra 1/6. 1/6 sine, this needs to scoot over, of 2 times t minus 2 pi. And both these terms are multiplied by the unit step function with the same argument, t minus 2 pi, t minus 2 pi, okay? Plus, and then this term actually ends up being even easier because there's already an s up top. So the inverse Laplace is going to involve cosine 2t. You don't need a 2 up top. Only for sine, you need k up top. So this is going to be cosine 2t. Good? Honestly, I didn't care if they just left it this way. But to completely simplify t minus 2 pi, we could change that back to t because these are both functions involving sine whose period is 2 pi. But if they jumped straight to this form, then they'd lose points because I wouldn't know that they remember how to find the inverse Laplace correctly. Because say instead you had some sort of different function here where it ended up being like e to the negative t minus 2 pi, then it wouldn't simplify back to just t at the very end. So I wanted to see that they knew how to apply the translation theorem correctly. Okay, so if they stopped at the line above, that's cool. If they jumped straight here, -1. Yep. I don't know what you know if you don't show me on a test. So think that when you're a student. If you thought it and then you simplified it, are you going to lose points? Did you not show everything that you know? In terms of the content of the course, like I don't need to see them FOIL. Who cares, right? I don't need to see them find partial fraction decomposition if they can do the cover-up method in their head. I want to see that they know their differential equations. So I want to see that you know the translation theorem. If you don't show me that you know it's t minus 2 pi before it simplifies, that's a problem. That's a big problem. Okay. Anyways, moving on. Here's another differential equation. What kind is it? It's first order. See that? Okay. First order, it's not looking homogeneous. Maybe you check if it's exact, and it's not. So guess what? It's separable. Yeah. Okay, so let's separate this. I'm going to move over nobody. I'm just going to start separating. So we've got sine x over 1 plus cosine x dx equals just 1 over e to the negative y plus 1 dy. Okay, so let's integrate both sides now. Beautiful. On the left-hand side, we can let u be 1 plus cosine x. Then du is just negative sine x dx. So this will become integral negative 1 over u du Ooh, so negative ln absolute value 1 plus cosine x. I'll save putting plus c on the right. Okay. Now, how to tackle this integral. Let's first multiply everybody through by e to the y. And then maybe things will reveal themselves. 1 plus e to the y dy. We can make a substitution as well. Don't use u. You already used it up in the problem. So let's let t equal the denominator. 1 plus e to the y. Then dt is e to the y dy. Beautiful. So then we'll have integral 1 over t dt. So it's just going to be ln absolute value 1 plus e to the y plus c. Okay, you can solve for c now or later. I was just so excited I went for it now. Y of 0 is 0. So negative ln of 2 equals ln of 2 plus c. So c equals negative 2 ln of 2, which is negative ln of 4. Okay, so I'll substitute that back in. If this is negative ln of 4, let me move it over there. They want to be reunited and happy. So positive ln of 4 minus ln absolute value 1 plus cosine x equals ln 1 plus e to the y. That's not going to be negative. So I can just drop the absolute value there. I can combine these into a single logarithm. So ln 4 over, now let's think. Cosine is bounded between negative 1 and 1. So I don't need absolute value there either. Oh, fabulous. 1 plus cosine x equals ln 1 plus e to the y. And then natural log is a 1-to-1 function. So because of that, we can set the arguments equal to each other. So 4 over 1 plus cosine x equals 1 plus e to the y. That looks mediocre. The snazziest final answer is 1 plus e to the y times 1 plus cosine x is 4. Yep, there it is. Beautiful. Mwah. Love it. Love, love, love. Okay, shall we move on? Use any appropriate method to solve the differential equation. This one is non-homogeneous, second order constant coefficients. Yep. So we're going to solve it similarly to the homogeneous differential equation. That was question number 1, finding the characteristic equation for the homogeneous. And then I'm going to use the annihilator method to find the particular solution. Okay? So what I'm going to do, jump right in. Let me rewrite the differential equation in terms of differential operators. So it'll become d squared plus d plus 1 times y equals x sine x. Now you can kind of skip solving the homogeneous first if you're very careful about distinguishing the roots from the characteristic equation that are for the homogeneous versus the roots for the annihilator for the non-homogeneous portion. So if you do it like me, you can save yourself some time, okay? What is the annihilator for x sine x? Well, remember, sine x is annihilated by d squared plus 1. And then since we have x to the first, this is going to be annihilated by d squared plus 1 squared. So if I apply this linear operator, I usually call it L1, to both sides, distinguish it somehow. Like, so you know that the roots from that differential operator are to annihilate x sine x. Okay, this all applied to y will give us 0. So now let's write the characteristic equation. So it'll be m squared plus 1 squared times m squared plus m plus 1, you don't have to write y anymore, is 0. Finding the roots, be careful, these are from the annihilator. So m equals plus or minus I twice. And then for this, we'll need the quadratic formula. We just did it in the first problem. So it's negative 1/2 plus or minus I rad 3 over 2. So use these to construct the solution for the homogeneous, for your complementary function. And then this will help me find the form of the particular solution. Okay, so here we go. Y equals C1e to the negative x over 2 cosine rad 3 over 2x plus C2e to the negative x over 2 sine rad 3 over 2x plus So alpha is 0, beta is 1. So we'll have, I'm not going to do C3, C4, C5. I'm just going to jump to A, B, etc. So I'm ready to find the coefficients. So this will be A cosine x plus B sine x. And then these are duplicate terms, so I'm going to add an x again and rewrite. This will be Cx cosine x plus, I'm going to skip D so we don't confuse it with our differential operator. So Ex sine x. Okay, this is Yp. Now I need to solve for ABCE, and I'll do that by substituting in. So I'll take two derivatives, plug it in, and then solve the system to get my coefficients. This part is where you have to really be careful. Okay, so Yp prime will be negative A sine x plus B cosine x plus C cosine x minus Cx sine x plus E sine x plus Ex cosine x. And then Yp double prime negative A cosine x minus B sine x minus C sine x minus C sine x minus Cx cosine x plus E cosine x plus E cosine x minus Ex sine x. Let me clean this up, right? We've got a lot of like terms. So negative A cosine x minus B sine x minus 2C sine x minus Cx cosine x plus 2E cosine x minus Ex sine x. Woohoo! Okay, let's plug this all into the OG differential equation. Y double prime plus Y prime plus Y is X sine X. Is that really what it was? Oh yeah, okay. So what do we have here? Negative A cosine X minus B sine X minus 2C sine X minus Cx cosine X plus 2E cosine X minus Ex sine X plus negative A sine X plus B cosine X plus C cosine X minus Cx sine X plus E sine X plus Ex cosine X plus Y, so A cosine X plus B sine X plus Cx cosine X plus Ex sine X equals X sine X. Okay, whoo! So we got to solve for ABCE. So let's see what the coefficients are of all the terms that involve cosine X. Not X cosine X, just cosine X. Got all those, and this one. So actually these cancel, right? Yeah, so we've just got 2E plus B plus C, and there's no cosine X's on the right, so that's 0. Okay, sine X. Who has sine X? You do, you do, you do. E sine X, B sine X, is that it? Yeah, B sine X cancels. So it's just negative 2C minus A plus E is 0. Okay. X cosine X. Who has X cosine X? You do. You do. You do. Except these cancel. So then just there's E. Oh, one more. No. There, there, there. It's just E is 0, right? Did I get everybody? Okay. So if E is 0, then B plus C is 0, and negative 2C minus A is 0. Okay. And then X sine X, that better be everybody else. I need another color. Oh no, let's just do black. x sine x, and then these cancel. So these are gone. So negative cx. So negative c is 1. So c is negative 1. So if c is negative 1, then a is 2 and b is 1. Woohoo! Okay, let's put it all together. So y equals c1 e to the negative x over 2 cosine rad 3 over 2x. Again, they could have factored out the e to the negative x over 2. I don't care. c2e to the negative x over 2 sine rad 3 over 2x plus 2 cosine x plus sine x minus x cosine x. Okay, sorry for the long pause earlier. I thought I made a mistake. I can't find if I went wrong, but I just felt not good. It's always important to have a little bit of healthy paranoia while doing math, but don't be so paranoid that you just can't proceed and you start second guessing everything you do. Okay. Use any appropriate method to solve the differential equation. Ooh, finally, this one is exact. Yep. Okay, to see it, let's first rewrite it. Let me multiply through by dy. Then we'll have x squared y cubed minus 1 over 1 plus 9x squared dx plus x cubed y squared dy is 0. Let's verify that it's exact. Okay. So this is m. This is n. So let's take partial of m with respect to y. It's going to be 3x squared y squared. And then check what's del n del x. 3x squared y squared. Oh my god, they're equal. Yay! So it's exact. That means m is the partial derivative of f with respect to x. So you're just going to integrate with respect to x. You don't even really need to write an integral sign or anything like that. Just anti-differentiate term by term. So f of xy would be 1/3 x cubed y cubed minus, this would be 1/3 tan inverse of 3x plus possibly some g of y, right? Okay, now n is the partial with respect to y, which is x cubed y squared. So anti-differentiate with respect to y, f of xy would be 1/3 x cubed y cubed plus h of x. Now compare. This is here. This is basically my h of x, and then I don't have a g of y, no problem. So our solution f of xy is 1/3 x cubed y cubed minus 1/3 tan inverse 3x plus c. Another way you could write it, you don't have to put f of xy, you can just say all of this equals c. You've got some options. I mean, this is the form that you write it in when you're in Calc 3 and you're finding the potential function. So you have a little bit of options. Okay. Use any appropriate method to solve the differential equation. It's Cauchy-Euler. And then also, oh my God, someone who turned in the test first noticed something. It's pretty cool. I'll show you their little shortcut, okay, when I finish doing Cauchy-Euler. And you're going to be mad because it takes 2 seconds with the little shortcut. Anyways, solving it as Cauchy-Euler. First, let me solve the homogeneous equation. So xy double prime plus y prime equals 0. And you might say, wait a minute, Professor V, it doesn't fit the criteria for being Cauchy-Euler. This should be squared and this is missing an x. Yeah, but it's fine. Like I can make it Cauchy-Euler if I multiply everybody by x. But then I'm just going to cancel it out anyways later on. So I don't need to waste time doing that. But just know if the power on x doesn't match, the order of the derivative, but it's by the same amount that it's off for every single term, it still can be solved as Cauchy-Euler, okay? So we assume a solution of the form y equals x to the m. So y prime is going to be m times x to the m minus 1, and then y double prime would be m minus 1, x to the m minus 2. All right, substituting all that in, we'll have x m minus 1, x to the m minus 2 plus m times x to the m minus 1 is 0. Now I'm going to factor out x to the m minus 1, and then we'll have m squared minus m plus m is 0. So these guys cancel. I'm going to assume x isn't 0, so we'll choose the interval for our solution to be 0 to infinity. So we're just left with m squared is 0. So m is 0, 0, repeated root. So the solution will have the form y equals c1 x to the 0 plus c2 x to the 0 ln of x. So basically y is c1 plus c2 ln of x. Now we have to do variation of parameters since this was non-homogeneous. We have x over here, so this is y1. y1 is just 1, and then y2 is natural log of x. Good? Okay, now before you jump into variation of parameters, make sure it's in standard form so you can identify f of x. It's not right now. I got to divide everybody by x. So xy double prime plus y prime is x. If you forget this step, you will cry because the next part won't work. So this one right here is our f of x that we're going to use for variation of parameters. Okay, so let's find the Wronskian. So we'll have y1 and its derivative, and then y2 and its derivative. And then let's find this determinant, 1 over x. And then w1, now I'm going to put 0 and then f of x. Second column unchanged. This determinant is negative ln of x. And then w2, first column from w unchanged, second column 0, 1. Oh, I love it. This is just 1. Okay, so now u1 prime is w1 divided by w. So it's going to be negative x ln of x. So u is going to be integral negative x ln of x dx. Now to evaluate this integral, we need to use integration by parts. You can still use the tabular method, even though you don't have like a polynomial times an exponential. Let me show you what you could do. I like tabular so much. It's just so clean. So d has to be ln of x. And then I is negative x. This derivative is 1 over x, and this is negative 1/2 x squared. This is just the same thing as normal by parts. I'm just not writing out u and dv. I don't know, my brain just likes this a lot better. And then remember, the signs alternate. Have this product here. So it'll be negative 1/2 x squared ln of x plus 1/2. Now we have integral x dx. That's not bad. So what is this? Negative 1/2 x squared ln of x plus 1/4 x squared. Don't worry about writing the plus c. And then u2 prime is going to be w2 over w. So that's just x. So u2 is 1/2 x squared. Okay, so particular solution yp is u1 y1 plus u2 y2. So negative 1/2 x squared ln of x plus 1/4 x squared times 1 plus u2 1/2 x squared times y2 is ln of x. I need another page, if you'll forgive me. Okay, so notice these are actually the exact same term. They'll cancel out. Yep, and I'm just left with 1/4 x squared. And so y is our complementary function plus particular solution. So y is c1 plus c2 ln of x plus 1/4 x squared. Now, are you ready for the super shortcut that someone did on the exam? Okay, let's go back, look at the original differential equation. Xy double prime plus y prime equals x. Xy double prime plus y prime equals x. Observe that the left-hand side is the derivative with respect to x of x times y prime? Yes, if you do the product rule, leave x alone, take the derivative of y prime, you get y double prime, plus derivative of x is 1, leave y prime alone. What does that mean for us? Well, we can integrate both sides now with respect to x. Okay. On the left-hand side, we'll just have xy prime equals 1/2 x squared plus, I'll just say c1. Now what do we do from here? Divide everybody by x. So y prime is 1/2 x plus c1 over x. Well, if that's y prime, that's the same as saying I have dy dx over here. Now we can make this separable, move the dx over. So dy is 1/2 x plus c1 over x dx. Integrate, integrate. Then we have y is 1/4 x squared plus c1 ln. You would put absolute value of x unless you stated we're on the interval from 0 to infinity. Then you could just put x plus c2. And then look at what we had using Cauchy-Euler and variation of parameters. It doesn't matter which one's c1, which one's c2. There we go. Same thing. And the student wrote even less. I mean, they didn't write all this stuff. From here, they just integrated and ended up here, and they were done in 2 seconds. So people who turn the exam in first, it's either like one of 2 things. They really, really know their stuff, or also the student who knows nothing turns it in usually very, very early on. Although some sit in their shame and wait for someone else to turn it in, and then they turn in their test with absolutely nothing on it. Those are things, you know, I've observed over 15 years. It's always the same. But brilliant. I loved it. It was so exciting. I was like, how did he finish so fast? And then when I saw, I was like, ugh, we love to see it. Okay. Find solutions of the differential equation in the form of power series in x. Here we go. Assuming we have a solution of the form y equals the sum n equals 0 to infinity c sub n times x to the n. So since this is a second order differential equation, I'll differentiate this power series twice. Y prime is going to be the sum. Don't forget to shift the index up by 1, n equals 1 to infinity, c sub n times x to the n minus 1. And then once more, we have the sum n equals 2 to infinity, c sub n times n minus 1 times x to the n minus 2. Now we'll substitute these into our differential equation. So y double prime, we have the sum n equals 2 to infinity, c sub n times n minus 1, x to the n minus 2, plus y is the sum n equals 0 to infinity, c sub n times x to the n. And this all equals 0. Okay, first order of business in order to solve is we need the power on x to match. So how do we adjust? I'll shift the index of summation where it starts on this one to go 2 lower. That way this will go up by 2. So up by 2. Everywhere there's an n, I'm going to replace it with n plus 2. And then this will now start at n equals 0. Okay, I'm just going through quickly. If you want more explanation, then you can watch the video lecture on this topic. So we'll go n equals 0 to infinity, c sub n plus 2 times n plus 2 times n plus 1 times x to the n plus the sum n equals 0 to infinity, c sub n times x to the n is 0. So now we're so happy we have x raised to the n in both of our expressions involving sigma. Then the next order of business is I need to make sure that the index of summation starts at the same value of n. And lucky for us, they already do. So we have no extra work to do. Okay, so then we're going to rewrite this, basically factor out the sigma, n equals 0 to infinity, and the x to the n, but I'll put that at the end. So then this is c sub n plus 2 times n plus 2 times n plus 1 plus c sub n. All of this times x to the n is 0. Now x isn't going to equal 0. That would just give us a trivial solution. So then the only way that this sum here, much better, could be 0 is if all the coefficients are 0. So c sub n plus 2 is equal to negative c sub n over n plus 1 times n plus 2. Now I'm going to list out however many terms I need until I see a recurrence relation. Okay, where do I start plugging in n? Well, this starts at 0, so that's where I'm going to start. So n equals 0. C sub 2 in that case would be negative C0 over 1 times 2. Okay, just leave it like that. Next, n equals 1. So C sub 1 plus 2, that's going to be C sub 3. That would equal negative C1 over 2 times 3. And I think it's a good idea to remind yourself C2 is the coefficient on the x squared term. C3 is the coefficient on the x cubed term. Because we're going to put everything together, coefficients with x raised to whatever power, in just a minute. Okay, keep going. N equals 2, that would be C4. That's negative C2 over 3 times 4. But I have C2 right here in terms of C0. So if I replace it with negative C0 over 2, then this becomes positive C0 over 1 times 2 times 3 times 4. Yes? Okay, good. And then continuing, n equals 3. That would give me C5, which would be negative C3 over 4 times 5. But C3, I have it right here in terms of C1. So let me substitute that in. Then that's going to give me positive C1 over 1 times 2 times 3 times 4 times 5. Very nice. Okay, let's do a few more, but I'm feeling pretty good. Like I can already see a pattern. Hopefully you can too. N equals 4 is going to be C6, which is negative C4 over 5 times 6. But if we go back, substitute in C0 over 4 factorial for C4, this becomes negative C0 over 6 factorial. Very good. And then n equals 5. Maybe after this we'll stop. C7 is negative C5 over 6 times 7. But go back, replace C5 with C1 over 5 factorial. This will be negative C1 over 7 factorial. So here's the big takeaway. All of the even coefficients, they are dependent on C0, right? Can you see? So C2, C4, C6, yes? And then the odds depend on C1. So we have here C1 for C3, C1 for C5, C1 for C7. Let's see if we can write out a rule in just a minute. And then also let's remind ourselves, like this is the coefficient on x to the 4th, x to the 5th, x to the 6th, x to the 7th. Now, we started with C2, and everything's in terms of C0 and C1. So we get as freebies C0 x to the 0, which is just C0, and C1 x to the 1st. So those are kind of automatically given to us. So now let's write out everything that we have. So y equals, I'll start with C0 plus C1x minus, okay, I'm going to think of this as negative C0 over 2 factorial to try to get the pattern going, times x squared. Next term would be minus C1 over 3 factorial x cubed plus C0 over 4 factorial x to the 4th minus C1 over 5 factorial x to the 5th plus yada, yada, yada. So at this point, hopefully you can see things are turning out beautifully. Let me factor out C0 from all the terms that contain it. So we'll just have 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th, etc. That's all we did. Plus C1 times x minus x cubed over 3 factorial. Should that not be minus? Did I make a boo-boo? Yeah, this one's positive. I'm so sorry. Plus x to the 5th over 5 factorial plus yada, yada, yada. Okay, and then let's write out the rule for those terms in sigma notation. Let's write out the infinite sum. So hopefully you recognize it's n equals 0 to infinity. It's alternating, so we'll have negative 1 to the n All of the powers on x are even, so we have x to the 2n over 2n factorial. Plus c1, who is this? This is the sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And that's enough, right? We found a solution as power series in x, but hopefully you recognize these are very famous power series, very famous Maclaurin series. This is actually c0 times cosine of x plus c1 times sine of x. Oh yes. And remember our original differential equation, it was second order, homogeneous with constant coefficients. You could just solve it by finding the characteristic equation, m equals plus or minus I. So then we would have y equals, in this case, alpha is 0, beta is 1, e to the 0x times c1 cosine x plus c2 sine x. And so we get y is c1 cosine x plus c2 sine x. Same thing. But they had to solve with power series for this particular problem per the directions, okay? This is a good way to confirm. This is just to verify. Yay. All right. Very, very nice. Last problem on the exam. Find two linearly independent power series solutions about the ordinary point x equals 0. List the first four non-zero terms of each linearly independent solution. So here we have x squared minus 1 y double prime plus 4xy prime plus 2y equals 0. We're just finding a solution around an ordinary point x equals 0. So we're going to assume a power series solution of the form y equals the sum n equals 0 to infinity c sub n times x to the n. So we already have y prime and y double prime from before. I'm just going to sub in everything. X squared minus 1 times the sum n equals 2 to infinity c sub n times n minus 1 x to the n minus 2 plus 4x times the sum n equals 1 to infinity c sub n times x to the n minus 1 plus 2 times the sum n equals 0 to infinity cn x to the n is 0. So remember, first order of business is we want to simplify and then get the powers on x to match. But don't worry about the powers on x matching just yet, because we have these x squared minus 1 and 4x to distribute. That'll affect things, so don't start shifting just yet. Distribute first. So if I distribute x squared through, this will now be x to the n. So we have the sum n equals 2 to infinity c sub n times n minus 1 times x to the n minus the sum n equals 2 to infinity c sub n times n minus 1 x to the n minus 2 plus the sum n equals 1 to infinity. I'll have 4cn times x to the n now, not n minus 1, plus the sum n equals 0 to infinity. I like putting, normally I'm like, take the constants out, not here. It's too dangerous. I don't want to forget them later, okay? All right, so let's see. Everybody is x to the n except here. So let's shift that one. So I'm going to add 2 everywhere I see n. And then this will start now at n equals 0 instead. And then we're good. So we have the sum n equals 2 to infinity c sub n times n minus 1 x to the n minus the sum n equals 0 to infinity c sub n plus 2 n plus 2 n plus 1 x to the n plus, and then the rest don't change. I told them, you know, you can skip steps here. It's just a wee bit dangerous because there's so much going on, but some of them are just rock stars. They'd probably be fine. Okay, good. Now we have x to the n. Woohoo! Next order of business. All of these need to start at the same place. You're not going to shift any indices because then that would undo what you just did. And we want to preserve the fact that all of these are beautiful, beautiful x to the n's. Don't mess that part up. So what do? Well, whatever one starts at the highest index, n equals 2, that's where the rest of them are going to need to start. So I'm going to write out n equals 0 and 1 separate from the sum. So this one can start at 2, same thing here, same thing here. Okay, so here we go. This first one, we don't have anything to do. I'm just going to rewrite it. Okay, minus. Now I'm going to write the n equals 0 term separately. So it's going to be, let me put parentheses. Could be dangerous. C2 times 2 times 1 times x to the 0. I'm also going to write n equals 1 separately. C3 times 3 times 2 times x to the first. Now I can start this guy at 2. And because I wrote 0 and 1 by themselves. Oh, they're so grown. They get to just break free from the sum and do their own thing. Okay, great. All right, over here, same deal. Write the n equals 1 term separately. So plus 4c1 times 1 times x plus, and then now you can start this guy at 2, 4cn times n times x to the n, plus, ooh, I gotta write 2 terms separate, not bad, 2c0 x to the 0 plus 2c1 x to the first, plus, then we're starting n equals 2 to infinity, 2cn x to the n is 0. Woohoo! Okay, now everything's so fantastic. We've got the sum n equals 2 to infinity. So basically you're going to factor that out, and then you're also going to factor out the x to the n, and just write everything as one big sum. And then you're going to have the little rando terms doing their own thing. 1, 2, 3, 4, 5 of them. Look at that. Okay, so we've got the sum n equals 2 to infinity Cn times n minus 1 minus Cn plus 2 times n plus 2 times n plus 1 plus 4Cn times n plus 2Cn all times x to the n plus the little random guys minus 2c2 minus 6c3x plus 4c1x plus 2c0 plus 2c1x, this all equals 0. Well, we're going to break this into 2 parts now. This is only true if this expression equals 0 and this combination here of coefficients equals 0. Okay, so let's just deal with this portion here. Negative 2c2, I can combine like terms, can't I? Right here. Because we've got 6c1x. So minus 6c3x plus 6c1x plus 2c0 is 0. Okay, just treat it like when you're solving for coefficients, when you're doing partial fraction decomposition, you basically have like ax plus b. This is 0 though, this is 0. So equating all of the constant terms, they must equal 0. Like negative 2c2 plus 2c0 is 0. That only is true if c2 equals c0. And then here's all the terms that are coefficients on x, but I don't see any x's on the other side. So negative 6c3 plus 6c1 is 0. So that's only true if c1 equals c3. Okay, then for the exciting part, let's set this all equal to 0. Okay, and have no fear, it cleans up ever so cutely. It really does. I'm going to factor out Cn while I'm at it. Cn times n minus 1 plus 4n plus 2 equals C sub n plus 2 times n plus 2 times n plus 1. And then, look at this. This is n squared minus n plus 4n plus 2. Which is n squared plus 3n plus 2. Okay. Always isolate the higher coefficient, like c sub n plus 2. So I'm going to get that one by itself. So c sub n plus 2 equals c sub n times n squared plus 3n plus 2. But wait a minute, you guys. Isn't n squared plus 3n plus 2 equal to n plus 2 times n plus 1? Yes, it is. Yes, it is. So then we have c sub n plus 2 equals c sub n. Wow, I was too nice on the exam. I was way too nice. Okay, where do I start plugging in, right? What value of n do we start at? Come back here. It starts at n equals 2, so that's where we start. So C4 is equal to C2, but don't forget, we learned earlier C2 is C0 and C1 is C3. Or I should say it the other way around. C3 is C1. So this just is C0. And then n equals 3, then we get C5 is C3, which is just C1. N equals 4. All the evens are equal to C0, and then all the odds are equal to C1, etc., etc. So I think we got this. You only needed to list the first 4 terms for each linearly independent solution. So y equals, you always have C0 x to the 0 plus C1 x to the first plus C2 is C0 x squared, C3 is C1 x cubed. Keep it going, just alternate. C0's on the evens, C1's on the odds. Oh, so relaxing. I should have picked a harder one. I don't know, but they did take a while. So y is C0 times 1 plus x squared plus x to the 4th plus x to the 6th plus C1 times x plus x cubed plus x to the 5th plus x to the 7th. Okay, so my 2 linearly independent solutions are right here. I'll call them y1 of x and y2 of x. Let's just be proper. I'll rewrite them. They didn't have to, but it bothers me to not be fully thorough when we've come this far, you know? Why would you not finish it beautifully? X plus x cubed plus x to the 5th plus x to the 7th. I mean, we might as well list 5 terms, but they only ask for 4. Let's not chance it by doing too much and then getting it wrong. Always tell yourself that during an exam. Okay, that's it. That was the set of required 10 questions. Then I put a generous amount of extra credit just to give them options. I wanted them to be at a math buffet when taking this exam. That is how much I love this class. I might do a story time and tell you guys why they were my favorite class in all my years of teaching. And I'm not emotional, but I did cry saying goodbye to them. And I cried another time too, handing back their exams. They really were that spectacular. Okay, use any appropriate method to solve the differential equation. So this is third order, constant coefficients, not homogeneous, but we don't have an annihilator for tan x. So we're going to go ahead and use variation of parameters to solve this guy. I'm trying to think if there was anything else that would have worked. Okay, so let's first solve the homogeneous equation, y triple prime plus y prime is 0. Characteristic equation would be m cubed plus m is 0. Take out an m, and then you have m squared plus 1 is 0. So the roots of our characteristic equation are 0 and plus or minus I. So we get y equals c1 plus c2 cosine x plus c3 sine x. And then I'm going to need to construct my Wronskian. So y1 is 1. I'll call my y2 cosine x. And I'll call my y3 sine x. Okay, so list your functions. 1, cosine x, sine x. Now take the derivative twice. Negative sine x, negative cosine x, cosine x, negative sine x. Now when you find the determinant, you can expand along any row or column. For goodness sake, please use this column. And it's just going to be 1 times sine squared x minus negative cosine squared x. So that's just 1. Beautiful. Okay, W1, I'm going to take the first column, replace it with 0, 0, and then f of x. What's f of x? Tan x. The rest of the columns are unchanged. So cosine x, negative sine x, negative cosine x, sine x, cosine x, negative sine x. Still, you can use this first column to expand along. We're going to have tangent x times the determinant of the 2 by 2 that results from deleting this row and column, cosine squared plus sine squared is 1. So this is just tan x. Look how relaxing. W2. Now the first column goes back to being 1, 0, 0. Then we have 0, 0 tan x. And then sine x, cosine x, negative sine x. I would still expand along the first column. So you have 1 times 0 minus tan x cosine x. But that's just going to give us negative sine x. And then lastly, W3, 1, 0, 0. Second column is cosine x, negative sine x, negative cosine x, and 0, 0 tan x. I'd still expand along the first column. So this is gone, negative sine x times tan x minus 0. So negative sine x tan x. That doesn't simplify. Oh well. Okay. And then the beautiful thing is W is just 1. So U1 prime, U2 prime, U3 prime are equal to W1, W2, W3 respectively. So just in case you forgot, U1 prime is W1 divided by W, but the Wronskian is just 1. So it's just tan x. So that means U1 is going to be integral of tan x dx. That one you should just have memorized. Ln absolute value secant x. U2 prime is negative sine x, so U2 would just be positive cosine x, and then U3 takes the most amount of work, but it's still not a lot. U3 prime is negative sine x tan x. So U3 is integral negative sine x. I'll write tan x as sine x over cosine x, and you might feel a wee bit stuck. No U sub is working out right now. You go, oh, shucks. So sine squared x dx over cosine x. And then let's just replace sine squared with 1 minus cosine squared. You know, like what else can one do in such a situation? They've given me no choice. Let's flip the order of subtraction so we get rid of that minus sign, and then watch this. We're splitting the cosine in the denominator. Bada bing, bada boom. And then you've got integral cosine x. Oh, I know your antiderivative. Perfect. Minus secant x. I know that antiderivative. Do you? Yes, Professor V. Oh, good. I was worried for a hot second. How am I out of space? Somehow it happened. Okay. Sine x minus antiderivative of secant x, natural log, absolute value, secant x plus tan x. We don't put the plus c's in this. I know I always feel a little ill, but in the video lecture I show why it's not necessary. So just move on with your life. Trust that it's not needed. Watch the video if you don't believe me. U1y1. Do you need me to remind you? YP is U1y1 plus U2y2 plus U3y3. Okay, beautiful. Plus cosine x plus sine x times all that stuff up above, sine x minus ln absolute value secant x plus tan x. Okay. Notice, please notice, this is sine squared x, this is cosine squared x, so that's just 1. How fancy. So this is 1 plus ln absolute value secant x minus sine x ln absolute value secant x plus tan x. Do I have everybody? Yeah, good. Okay, so let's put it all together. It's the complementary function plus the particular solution. So we had C1 plus C2 cosine x plus C3 sine x. You know, I should have put a y sub c there. Forgive me. Plus all of this. Sorry, I'm just a little tired of writing, if you'll allow me. Okay. So here's what I want you to notice. C1 is a constant. 1 is a constant. they should get absorbed to make a new constant for simplification purposes. What can we call it? C4, C0, whatever. C, you do whatever makes you happy. I'll just say C4 plus C2 cosine x plus C3 sine x plus ln absolute value secant x minus sine x ln absolute value secant x plus tan x. And then you have to tell the people, who is this new C4? How did it suddenly come onto the scene? It's 1 plus C1. You're like, calm down. But you have to tell the people who it is. Okay, good. More good stuff. Use Gauss-Jordan elimination to solve the following system. I put this on there because we did go over row operations and whatnot, and I thought it would be relaxing for some. Anyways, there is crossover between differential equations and linear algebra, so that's why we covered this topic. You should end up with, I'm not even gonna go through it. I think at this point everybody can row reduce well. If not, I have plenty of videos on it, so go ahead and watch those. And you end up with 3, 1, negative 5. So that's the solution. 3, 1, negative 5. That ordered triple. Independent, consistent. Not that you needed to name all that. Okay, last extra credit. Dun, 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 dun. Use the method of Frobenius to obtain 2 linearly independent series solutions about the regular singular point x0 equals 0. List the first 3 non-zero terms of each linearly independent solution and then form the general solution on the interval from 0 to infinity. Okay, so remember when we're using the method of Frobenius and we're finding series solutions about a regular singular point, we assume a solution of the form y equals the sum n equals 0 to infinity c sub n times x to the n plus r. A little different. Y prime then is the sum n equals 0 to infinity c sub n times n plus r times x to the n plus r minus 1. Because you have x to the n plus r, when you differentiate, you don't lose that first term. It's not a constant. So the index does not shift when you differentiate. And then y double prime is the sum n equals 0 to infinity c sub n times n plus r times n plus r minus 1 times x to the n plus r minus 2. Okay, here we go. Let's get locked in. 3x times y double prime, which I have right up there, plus 2 minus x times y prime. So the sum n equals 0 to infinity cn n plus r x to the n plus r minus 1 minus the sum n equals 0 to infinity cn x to the n plus r is 0. Okay, same strategy or goal as before. We want to distribute, and then we're going to try to get all the powers on x to match so we can factor it out. So this is the sum n equals 0 to infinity 3cn n plus r minus 1 x to the n plus r minus 1, right? Because I just brought inside x to the first. Plus the sum n equals 0 to infinity 2cn n plus r x to the n plus r minus 1 minus the sum n equals 0 to infinity cn n plus r x to the n plus r. And this last guy doesn't change, right? Minus the sum. It's squished, but I really don't want to bust out a second line. So here I go. Okay, good. So what should we make the exponent? It's really up to you. You could make them all n plus r, or you could make them all n plus r minus 1, because these two match and these two match. So it'll be the same amount of work. I decided to make everything n plus r minus 1. If you do it the other way and you make everything n plus r, don't worry. Things might look a little different. You'll still arrive at the same solution. That is why math is just the most beautiful topic to study. Really, really it is. Okay, but I don't mean to get on a tangent. Let's just start shifting. I'm not going to touch the first two then, okay? So the goal is n plus r minus 1, okay? So these ones I'm just rewriting, but I'm kind of trying to write them smaller so everybody will fit. I don't know if my efforts will be in vain or if they will work out. Okay, here we go. Focus, people, focus. So if these go down by 1, down by 1, down by 1, this needs to start at 1. Same thing, down by 1, start at 1. Okay, if you know this is a dangerous moment for you, write those little minus ones and whatnot to save you. C sub n minus 1, n plus r minus 1. X to the n plus r minus 1. Oh no, here it comes, a second line. I'm so disappointed in myself. C sub n minus 1, x to the n plus r minus 1. And this is all 0. Okay, no, we're not footloose and fancy free just yet. Everything needs to start at the same value of n. Always have to have everything start at the highest one. So I'm going to write the n equals 0 term separately on these guys. And then we should be in business, okay? So 3c naught times r minus 1 times x to the r minus 1 plus the sum n equals 1 to infinity 3cn n plus r minus 1 x to the n plus r minus 1 plus, now I'm going to write the n equals 0 term separately here. So 2c naught times r times x to the r minus 1 plus, now I can start at n equals 1 to infinity, 2cn n plus r, x to the n plus r minus 1. And then the last two, I don't have to do anything. So if you'll just allow me to copy paste, I'll be thrilled. And this, okay. Beautiful. So now what we can do, we can factor out the sigma, because it all goes n equals 1 to infinity. We can basically write this all with one sigma notation, and then also take out the x to the n plus r minus 1. And then I'm going to write out my initial equation. We don't need to write the x to the r minus 1. So initial equation, we have 3c naught times r minus 1 plus 2c naught times r is 0. Divide through by c naught, it can't be 0. So 3r times r minus 1 plus 2r is 0. I can factor out a r, and then I have 3r minus 3 plus 2 is 0. So r times 3r minus 1 is 0. So either r is 0 or 1/3. Those are my initial roots. Now for the rest of it, what do we have going on? We have the sum, n equals 1 to infinity, 3cn, excuse me, I almost forgot that part, n plus r minus 1 plus 2cn times n plus r minus cn minus 1 times n plus r minus 1 minus cn minus 1, just a bracket, is 0. Okay, so then I can go ahead, set everything in the brackets equal to 0. And let me factor out cn from the first two terms. And I can take out n plus r. Then we have 3 times n plus r minus 1 plus 2, and then that equals the other terms that have cn minus 1 in them. Factor that out, then you have n plus r minus 1 plus 1. Yeah. Okay, perfect. So then if I get cn by itself, that's cn minus 1 times n plus r divided by n plus r times 3n plus 3r minus 3 plus 2. And then notice these n plus r's cancel. So then we have cn minus 1 over, very lovely, 3n plus 3r minus 1. Oh, I like that so much. That was nice of me. There were much uglier problems that we did in the homework. Okay, so we just needed how many? The first 3 non-zero terms of each linearly independent solution. Okay, perfect. Well, the good news is you get a freebie. You get C naught x to the 0, right? So that's always good. Let's start with r equals 0. First initial root, r equals 0, and I'll put it in my recurrence relation. Cn is Cn minus 1 over, if r is 0, this is just 3n minus 1. Woohoo! What do I start plugging in for n? Where did my sum start? It started at 1. So that's where we're going to start. N equals 1. So C1 would be C naught over 3 minus 1. So C naught over 2. N equals 2. C2 is C1 over 6 minus 1. So that would be C naught over 2 times 5, or C naught over 10. And don't forget, we already have C naught x to the 0. This is C1 times x to the first, and C2 times x squared. So I already have the first 3 non-zero terms. Maybe your professor asked for 4. I don't know. What did they ask for? I'll do 4. C naught over 80. Yes, and this is on x cubed. So here's my first solution. y1 of x is C naught times 1 plus 1 half x squared. No, just x. I got too excited. Plus now 1/10 x squared plus 1/80th x cubed. And you have to say plus dot dot dot. There's infinitely many more terms. Okay, that's not bad. Now use the second initial root, r equals 1/3. And then I come back here, I'm going to substitute in 1/3. Oh, but that's so lovely because that's 1 minus 1 that cancels. So C sub n is just C sub n minus 1 over 3n. Okay, so then C1 is C naught over 3. C2 is C1 over 6, which is C naught over 18. C3 is C2 over 9, which is C naught over 162. I'm going through this like at an aggressive pace because I'm just solving it. I know they're curious to see how they did on the exam. If you actually need help learning the method of Frobenius, please believe I don't teach this way. I have a video lecture on it, so you can watch and I'll break everything down. If it seems like I'm working like a mad woman, I know. Okay, so that should be enough terms. Let's put it together. This one is y2 of x. Okay, here's where we're gonna have to like rename stuff, right? Because like what, they both have C naught. Oh, I didn't have to worry about anything in the front. I was negligent. We have x to the r, and x to the 0 is just 1 in this case. That's hanging out there. But in this case, r is 1/3. So we have x to the 1/3, and then we'll have times 1 plus 1/3 x, because remember this goes with x to the first, x squared, x cubed. So plus 1/18 x squared plus 1 over 162 x cubed plus infinitely many more terms. So then I did ask them in the directions to form the general solution on the interval from 0 to infinity. And just to make it really cute, right? So we're going to make a linear combination of these two solutions. And I'll rename C naught to be C1 to match the subscript on this function. And then I'll rename this constant to be C2 to match the subscript here. So the final answer should be y equals C1 times 1 plus 1 half x plus 1/10 x squared plus 1/80th x cubed plus C2 x to the r, x to the 1/3 times 1 plus 1/3 x plus 1/18th x squared plus 1 over, they didn't need this fourth term, so if you got it right on the extra credit and you're like, I didn't put that last term, don't worry, I'll give you your points, you're good. And that's it. Okay, if you need video lectures or a breakdown on any of the topics here or in differential equations, I'll link the playlist in the description. And A lot of them are members only or on my Patreon, so you need to join there to watch everything. All right, that's it. This was, I'm not even exaggerating, the best class of my entire teaching career. I will maybe record a video talking about why they were so amazing, and I hope they keep in touch with me. They're transferring to so many amazing universities. I teach at a community college, so I have students going to MIT, Princeton, Berkeley, UCLA, lots more, and I couldn't be more proud. So it was my honor to have a part in their educational journey, and I'm kind of saying this in case they, I think a lot of them are going to watch the video. I don't know if till the end, but I just want to thank them for working so hard. Okay, that's it. Don't forget to give this video a thumbs up. Subscribe if you haven't already. Follow me on Instagram and TikTok, Math with Professor V. I love you all.